So we've kind of seen how we can use a diode as a switch, but how about the BJT as a switch? In previous sections, we discussed the transistor as a linear amplifier. The second major application area is in switching applications. When used as an electronic switch, a transistor normally is operated alternately in cutoff and saturation. Below you can see the illustration of the basic operation of a transistor as a switching device. In part A, the transistor is in the cutoff region because the base emitter junction is not forward biased. In this condition, there is ideally an open between the collector and the emitter, as indicated by the switch equivalent to the right. In part B, the transistor is in the saturation region because the base emitter junction and the base collector junction are forward biased, and the base current is made large enough to cause the collector current to reach its saturated value. In this condition, there is ideally a short between the collector and the emitter, as indicated by the switch equivalent. Actually, a voltage drop of up to a few tenths of a volt normally occurs, which is the saturation voltage, VCE sat. So we can see all that in the diagrams below. Conditions for cutoff. As mentioned before, a transistor is in cutoff when the base emitter junction is not forward biased. Neglecting leakage current, all of the currents are approximately zero, and the voltage collector to emitter is approximately equal to VCC. So VCE cutoff is equal to VCC. Conditions in saturation then, when the base emitter junction is forward biased and there's enough base current to produce a maximum collector current, the transistor is saturated. Since VCE sat is very small compared to VCC, it can usually be neglected. So the collector current then becomes approximately the ratio of VCC to RC. The minimum value of base current needed to produce saturation then is IB min, which is IC sat over B over beta DC. So in this example, for the transistor switching circuit, what is VCE when Vin is 0? What minimum voltage of base current will saturate the transistor if beta DC is 200, and calculate the maximum value of the base resistor when Vin equals 5 volts. So take a look at our diagram. We can see VCC is 10 volts. We've got the collector resistor at 1K ohm and our other resistor and Vin. So when Vin is at 0, the transistor is in cutoff, and VCE equals VCC, which is 10 volts. Okay, so we're feeling the full 10 volts then. When the transistor is saturated, VCE is equal to approximately 0, so the collector current saturated is equal to VCC by RC. So 10 volts VCC, 1K ohm for the resistor gives us 10 milliamps for IC sat. The base current then minimum is IC sat by beta DC. So there's IC sat. Beta DC was given as 200, so 50 milliamps. So this is typically a value you would see in your curves. This is the value of the base current necessary to drive the transistor to the point of saturation. Any further increase in base current will drive the transistor deeper into saturation, but will not increase the collector current. When the transistor is saturated, the voltage base to emitter is equal to the barrier voltage, 7/10. The voltage across RB, then, the base resistor, is equal to Vn minus the potential, barrier potential, in this case 5 minus 7 tenths gives us 4.3 volts. The maximum value of the base resistor that will allow a minimum of current is 50 microamps. It's calculated by Ohm's law. The actual value should be much less. So if we use VRB by IB, Ohm's law, we get 86 k ohms.